Blood flows through the heart in one direction, from atria to ventricles and out large arteries. This is made possible by pressure changes caused by alternating contraction and relaxation of the heart. Blood moves through the heart according to pressure gradients, always from an area of high pressure to an area of lower pressure. Let's examine pressure changes in the heart throughout each phase of the cardiac cycle. The following graph depicts pressure changes in the heart chambers and arteries through time. This graph depicts pressure changes on the left side of the heart only. The left side of the heart pumps blood through the body's tissues, which requires tremendous force. The right side of the heart services the pulmonary circuit, which requires less pressure. The graph depicts pressure changes throughout the cardiac cycle in the left atrium, indicated by the purple line, the left ventricle, indicated by the blue line, and the aorta, indicated by the green line. This pressure graph depicts slightly more than one cardiac cycle. We'll arbitrarily decide to begin our cardiac cycle here, at the first arrow, right before this small increase in atrial and ventricular pressure. The second arrow then indicates the end of one cardiac cycle. We could have begun our cardiac cycle at some other point, but this range will be convenient because it occupies the center of our graph. We begin with atrial contraction, where the ventricle is relaxed and filling with blood. During this phase, atrial pressure, indicated by the purple line, is higher than ventricular pressure, indicated by the blue line. Blood always flows through the heart according to pressure gradients, from high to low pressure. We'll draw an arrow from the atrial pressure trace to the ventricular trace to indicate this pressure gradient. Blood moves from high pressure in the atrium to an area of lower pressure in the ventricle. Based on pressures alone, we might expect blood flow from the aorta to the atrium. But the aorta and atrium are not connected, so blood cannot flow between these two regions. Similarly, we might expect blood to flow from the aorta to the ventricle. However, the semilunar valve prevents this from happening. Heart valves, like the semilunar valve and the AV valve, prevent backward flow of blood through the heart, even when pressure gradients favor such flow. Once the ventricle is filled with blood, it begins to contract. This indicates the start of isovolumetric contraction. As the ventricle contracts, ventricular pressure begins to rise, which forces the AV valve closed. Valve events always occur at the intersection of pressure traces. So, for example, the AV valve closes when the ventricle trace crosses the atrium trace. Closure of the AV valve prevents blood from flowing backward into the atria, which is now at a lower pressure than the ventricle. Pressure is not yet high enough in the ventricle to open the semilunar valve, leading into the aorta. The semilunar valve will not open until the ventricle trace crosses the aorta trace in the next phase. Therefore, blood cannot flow backward through the heart while the semilunar valve is closed. During this phase, all valves into and out of the ventricle are closed. Eventually, pressure in the ventricle exceeds pressure in the aorta, forcing the semilunar valve open, allowing blood to be ejected from the ventricle into the aorta. This is called ventricular ejection. Notice blood is flowing from an area of high pressure in the ventricle to an area of lower pressure in the aorta. Although the pressure difference between the ventricle and aorta becomes small, the semilunar valve remains open and blood continues to flow out of the ventricle. Once pressure in the ventricle drops below the pressure in the aorta, the semilunar valve shuts, preventing blood from flowing backward into the ventricle. The sudden closure of the semilunar valve results in blood from the aorta rebounding off the closed valve, causing a transient increase in aortic pressure. This forms a notch in the aortic pressure trace, known as the dicrotic notch. Once again, the ventricles are completely closed chambers, the semilunar valves, and the AV valves are closed. This represents isovolumetric relaxation. As the ventricle continues to relax, ventricular pressure drops below atrial pressure. This pressure change results in the AV valve opening, allowing blood to flow from the atrium, which is at a higher pressure, into the ventricle at a lower pressure. This marks the beginning of ventricular filling, and another cardiac cycle will soon follow. Throughout the phases of the cardiac cycle, blood flows from an area of higher pressure to an area of lower pressure through one-way valves. Pressure gradients are caused by alternating contractions and relaxations of heart chambers. Blood flows into the ventricle during atrial contraction, from the ventricle into the aorta during ventricular ejection, and from the atrium to ventricle during ventricular filling. The opening and closing of one-way valves always occurs at the intersection of pressure traces on the graph. The valves open to allow blood to move through the heart from high to low pressure. The valves close to prevent blood from flowing backward through the heart, even when pressure gradients favor such flow.